Hi guys, in today's video we are going to learn about SIMD, Single Instruction Stream Multiple Data Stream Architecture. It is basically a part of instruction level parallelism module. During the previous video we have learned about the basic concept of instruction level parallelism and how to use loop unrolling to implement instruction level parallelism. Now, in SIMD architecture, you will learn how to apply or implement that instruction level parallelism in real computation. Just let me have a quick recap of the scenarios where instruction level parallelism phenomena can be used. Yes, just zoom it. If you can recall this example from the previous video, so you can find that although in programming language terms, here we have two instructions implicitly, but in explicit terms there are 100 arithmetic instructions. Okay, so if you try to run or execute these instructions in a SISD architecture machine, there the scenario is that you only have a single processing element which is capable of doing this addition task. Now think of an imaginary situation where what you do, you just increase the number of processing elements which are capable of doing addition task. What will happen? The result will be you will be able to complete this addition task in smaller number of clock cycles. For example, if you have a single processing element, then as there are 100 addition operations, you need 100 clock cycles to complete the entire task if a single addition requires 1 clock cycle to complete. But say now you have 25 such processing elements which are capable of doing the addition task for you. Okay, processing element index 0, processing element indexed 1, and this one is processing element with index 99. Now what you will do, you will send the first addition operation to the first processing element, second addition to the second processing element, and 100th addition operation to the 100th processing element. Now all of this can be done in a single go. So what is the takeaway? The entire addition task which has been defined in this for loop can be completed in a single clock cycle. This is the basic idea behind the implementation of SIMD array processors. Now let me go back to our SIMD array processor. Yes, here it is. So, what are the basic ideas behind SIMD array processor? In SIMD array processor, you will have large number of small or single processing elements. That means you will have a single processor where number of processing elements will be multiple. Each processing element might have its own memory, which you will study deeply later on in this video. Okay. Typically only connected to its neighbors. Why this is necessary? Just take a note of this. We will discuss this in a little detail. Why the processing elements need to be connected with its neighbors. Now there will be a single control processor issues each instruction. In turn, every processing element executes the same instruction on its local data at the same time. Next, some processors may be turned off on any instruction. This allows certain logical operations to be performed, such as branch type instructions. So this is a generalized schematic view of the SIMD architecture. Here you will have a control processor which will route the different instructions, whichever can take the benefit of instruction level parallelism to different processing elements. Why I am saying this? Just again carefully listen to what I am saying. What is the purpose of this control processor? The control processor will route the instructions to different processing element. Now, which instructions will be routed to different processing element? The instructions which can take the advantage of instruction level parallelism. Now, take an example. Say you have a program segment where the first instruction is something like int I equals to 100. Fine. And then you have a for loop where you have int j equals to 0, j less than 100, j plus plus, a j equals to bj multiplied with 3 limit. Now the first instruction is int I equals to 100. Then at the next line you have a for loop. Now just think for a while. Among the instructions in this code segment, which instructions are capable of taking the advantage of instruction level parallelism? Just think for a while. Okay, I hope now you have some thought in your mind. This int I equals to 100, this actually a standalone instruction which is a scalar instruction. This int I equals to 100 is not capable of taking the advantage of instruction level parallelism. But if you look into the for loop, as we have discussed in our previous video, here basically there are 100 instructions explicitly in a single instruction. Now, this for loop or instructions inside the for loop are capable of taking the advantage of instruction level parallelism. So, if you come back to this diagram, now the control processor will decide or cluster the instructions into two segments. The instructions which can take the advantage of instruction level parallelism, route them to different processing element. For example, the contents of this for loop will be routed to the different processing elements so that they can be executed parallelly in the same clock cycle. And you will have a scalar processor which will execute this standalone scalar instruction. In our example, it is int I equals to 100. So next, you can see here we have something called interconnection network. Now, question might arise, what is the purpose of this interconnection network? If you look at the different processing elements, you can find that all the processing elements are connected to one another via network interface through this interconnection network. In essence, they can communicate with each other. So, why this thing is necessary? This thing is necessary because sometimes situation might occur that, for example, say whatever computation is going on P2 might be necessary to be accessed by P1. In that scenario, there must exist some mechanism by which P2 can communicate with P1, and interconnection network is that medium. So let me move on. Just do one thing, read this portion carefully yourself and try to take the essence. Main advantage of this machines, that means SIMD machines, is the ease of programming. Ease of programming. Why? Because of this SIMD architectures, this type of for loop or loop type instruction execution has become simple. So now, to simplify your programming task, you can include more of these things in your programming course. The disadvantage is that they are specialized machines and not suited to all applications. Now, what is the justification behind this disadvantage statement? The justification is something like, if you have more and more scalar type instructions in your program, then the use of these processing elements are futile because your program is scalar in nature. Next, these architectures support the interesting model of data parallelism or instruction level parallelism. Okay, now I think we have discussed a lot about how instruction level parallelism can be implemented using this SIMD architecture. In data parallel computing, what happens? The parallelism lies in data, not in the control. If you can just notice this example once again, you can find that it is the nature of data which is providing this benefit called instruction level parallelism. How? Because there is no interdependency between the data. That's why you can execute them parallelly. So hence this line is again justified. In data parallel computing, the parallelism lies in the data, not in the control. Data parallel computing relies on the vector model of parallelism, which we are going to learn in this module itself later on. This model assumes multiple data and serial control. So next you have a diagram. This is the actual diagram or actual model of SIMD, which was coined by Flynn itself. I think you remember Flynn's classification, and this was the SIMD model coined by Flynn. So just have a deep look into the diagram. You have a scalar memory, then you have a scalar processor, then you have a vector processor. That means different processing elements are embedded into this processor segment. Now, if you have a scalar type of instruction like this, you will route that instruction to the scalar processor segment. If you have a vector type instruction or instruction which can take advantage of ILP, you will route that to the vector processor segment. So next, in this category, a more specialized implementation of SIMD processor is array processor. So just have a look at this diagram once again. It is similar to the diagram coined by Flynn. Just you have a segment dedicated to instruction issue, right? So it is basically nothing but your control processor, this thing. So what is the purpose of this instruction issue segment? It will broadcast the instructions to different processing elements. These processing elements are fabricated as an array. If you have n number of processing elements, then in this diagram you can see that they're subscripted like array. Array element 1 or processing element with subscript 0, then you have array element 1 or processing element with subscript 1, then up to array element n-1, that is processing element with subscript n-1. Then you have a global state module. You can see this here. Now what the control processor will do, it will broadcast the instructions through the broadcast channel. If the instructions are array type or can take advantage of ILP, then they will be executed in this array segment, and if they're standalone instructions like scalar instruction, they will be routed to scalar processor to be executed. Now have a look at the statement. In array processor architecture, a program consists of a mixture of scalar and array instruction, just as we did in our example. It is a mixture of scalar type instruction and vector type instruction. Then the scalar instructions are sent to the scalar processor. Scalar instructions will be sent to the scalar processor, and the array instructions are broadcast to all array elements in parallel. They can be executed parallelly. That means if your clock cycle is at tth instant, then A0 of our example can be executed in array element 0 at the same time. That means at the clock cycle t itself, array element 1 can handle A1, and then if you have array element 3, A3 can be routed to A3, array element 3 to get executed in the same clock cycle. So you can say that this broadcasting to all array elements in parallel is justified. The instructions are not interdependent, and as a result, the computations which are going on in different processing elements are also independent of one another. Now, array elements are incapable of operating autonomously and must be driven by control unit. Why? Because although you have the explicit instructions are independent of one another, it might be the case that this A variable is a part of a single data. In that case, you cannot offer them to be independent of one another from a perspective. So, array elements cannot be operated autonomously, and they must be driven by some control units, so that after computation task is complete, then they can be accumulated at a single place so that they can be used later on. Okay. Then you have a broadcast mechanism. Just have a look at this broadcast mechanism yourself and try to understand this. Then you have two different types of array processors actually, and this classification is loose one. They are classified in terms of memory elements they have. If you look into figure 4, which depicts array processor with shared memory, you can find that there you have processing elements 0 to n minus 1 and memory elements 0 to n minus 1. Now, basically, for a process to be executed in a processor, from our previous study, we know that it needs to access memory sometime during the operation. So, in this case, what happens? You can see that memory is basically independent of the processing elements. That means not a single memory segment is connected to a particular processing element directly. Rather, processing elements and memory elements are connected via a switching network or interconnection network. So, In this case, you can think of this memory module as a global memory module. That means any processing element can access any memory segment through the interconnection network by some protocols, which has been predefined by the designer. Then come to the next diagram. If you look into this diagram, you can find that different processing elements are connected to their native memory units. That means memory unit 0 is connected to processing element 0 natively. Similarly, memory unit 1 is connected to processing element 1, mem2 is connected to P2, and so on up to n-1. Now, these memory elements are native to the individual processing elements. But question might arise, can a memory element which is native to some processing element be accessed by another processing element if necessary? Say, for example, memory element 0 which is native to PE0 somehow need to be accessed by processing element 2. Will it be possible? Yes, it will be possible because all the processing elements are essentially connected to one another through interconnection network. If the protocol implemented by the designer permits, then this memory elements can be accessed by any processing element in exceptional scenarios. So, I hope you have got an idea of this two differently classified structures of array processors. Now, just look at the statements. The three major components of an array structure are array units or processing element units, the memory they access, and connection between the two. Now, you see, the connection is also an important part because, as we have discussed before, after the computation has been complete for this segment, for this for loop, then result have to be accumulated and have to be delivered as a whole. So, you need to collect the computational outputs which have taken place in different processing elements at a place and deliver it to the user. And this can be possible only through this interconnection network. Now, next, here some real-time facts have been told. If all memory is shared, if all memory is shared as in figure 4, then the switch network connecting the array units to the memory must be capable of sustaining a high rate of data transfer, since every instruction will require massive movement of data between these two components. Why? Because in this case, what will happen? Different processing elements will access all the memory segments in equal way. In that case, at certain point of time, it might occur that processing element 0 is accessing memory 0. Just after a few moments, Say processing element 1 makes a request for the contents of memory 0. So in this case, what will happen? There will be extra load on this data link which is connected mem0 to switching network. In that case, what have to be implemented? The data transfer rate will be very high. In that case, that data link must be capable of transferring data at a high rate. Otherwise, the computational task cannot sustain. Alternatively, if the memory is distributed, then the majority of operands will hopefully, not particularly, hopefully reside within the local memory of each processing element. That means if you use this architecture, then for most of the time, what will happen? The computations which are going to be performed in processing element, the related memory items will be stored in mem0 itself. And similar thing will happen for other processing elements also. In that case, the above problem, that means problem of sustaining a high rate of data transfer, gets mitigated somehow. So from this discussion, you can conclude that the design of the switching network is a critically important thing. Now, although this is included in this part, we are going to discuss this interconnection network part in multiprocessor architecture module because both are basically same. Now, this was all for this topic. Now I will tell you how to study this module. First, like the previous topics, you have to go through the study material. At first, you need to roughly study everything, then watch the video lecture, then once again come back to the study material and read it in between the lines carefully. Good luck. Have a great day.